Welcome to the lecture on implementation of multiple linear regression in R. To summarize, from the previous lecture, we looked at steps in building a simple linear regression model, where we looked at how to regress an independent variable with a dependent variable. As a part of this, we also looked at how to assess the model that we have built, and under that we looked at how to interpret the model summary and identify the significant variables, how to do residual analysis, how to check if the model needs refinement, and we built a refined model. In this lecture, we are going to extend all of this to multiple independent variable. So, it is called multiple linear regression, and in this we are going to build a linear model with one dependent and multiple independent variables. We are also going to look at the model summary and identify the insignificant variables and discard them and rebuild the model. We will also look at how to identify the subset of variables to build the model. This is called model selection. So, let us start by loading the data. So, the data set NYC is given to you in a CSV format, and to load the data set we are going to use the function read.csv. So, the inputs for the function read.csv, it is similar to what we saw in the previous lecture for read.dlim. So, read.csv reads the file in a table format and creates a data frame from it. So, the syntax is read.csv and the inputs to the function are file and row names. So, file is the name of the file from which you want to read the data, and row names is the vector giving the actual row names, could also be a single number. So, let us see how to load the data now. So, assuming nyc.csv is in your current working directory, the command is read.csv followed by the name of the file in double quotes. Now, once this command is executed, it will create an object nyc, which is a data frame. Now, let us see how to view the data. Now, view of nyc will display the data frame in a tabular format. There is a small snippet below which shows you how the output looks. So, I have price, food, decor, service and east as the 5 variables. So, say suppose if your data is really huge and you do not want to view the entire data, then we can use head or tail function. So, head will give you the first 6 rows from a data frame and tail will give you the last 6 rows from the data frame. So, now let us look at the description of the data set. We have already loaded it and we have viewed it, but we do not know yet what the description is. So, the data is about menu pricing in restaurants of New York City. So, y, which is my dependent variable, is the price of the dinner. There are 4 other independent variables. So, I have food, which is one of the independent variables. It is the customer rating of the food. Then I have decor, which is the customer rating of decor. Then I have service, which is the customer rating of the service, and east. So, east is whether the restaurant is located on the east or west side of the city. So, now our objective is to build a linear model with y, which is price, and with all the other 4 independent variables. Before we go on building a model, let us see if our data exhibits some interdependency between the variables. So, for me to do that, I am going to use a pairwise scatter plot. So, I am going to use same function plot which we earlier used. Now, since I have multiple variables, I am going to give the data frame as my input, and I am just giving a heading as pairwise scatter plot. On my right, this is the output you will get. So, we can see that all the variables are mentioned across the diagonals. So, when one moves from left to right, the variables on my left will be in the y axis and the variables above or below will be on the x axis. So, let us take the first row for instance. So, I have price on the left. So, price is in the y and I have food below. So, food becomes the x axis. Now, this is the plot for price versus food. Similarly, I have price versus decor and price versus service and price versus east. I am going to the next row, which is food on the y axis. So, if you take food versus decor, the data is randomly scattered. So, it does not show any correlation patterns, but whereas if you see for food versus service, you see strong patterns being exhibited here. So, let us see what the correlation is as such for all of these. So, correlation is the function, and Professor Shankar has told you how it is computed. So, COR is the function in R. I need to give the data set with all the variables. Now, round tells you to how many decimal points you want round off the number to. So, if I give round and I am giving the input as my correlation function, and if I am saying 3, it means round off the numbers to 3 decimal places. So, let us see how to interpret the output. So, the correlation for price versus price will always be 1. So, let us look at food and decor. So, the correlation between food and decor is 0.5, which is pretty low, but whereas if you look at food and service, it is almost equal to 0.8, which is quite high. So, we can see that food and service are correlated, but one of them can be dropped while building a final model. So, as we go along, let us see which of the two we have to drop. So, now let us go on to model building. So, like I earlier said, my dependent variable is only one here, and then which is denoted by y. I have several independent variables which are denoted by xi, and I could range from 1 to p, where p is the total number of independent variables. Now, let us see how to write this equation with multiple independent variables. Again, I have y hat, which is the predicted value. Now, I have beta naught hat, which is the intercept. Then I have beta 1 hat x1 plus beta 2 hat x2, so on and so forth, up to beta p hat xp. So, beta naught hat is the intercept, and beta 1 hat, beta 2 hat, etc. are the slopes. So, epsilon is the error. So, if you could recall from your earlier lectures, in OLS, the assumption is that error is present only in the measurement of dependent variable and not on the independent variable. So, independent variables are free of errors, whereas there is always some error present in the measurement of y. So, this epsilon is an unknown quantity which has 0 mean and some variance. Now, for any ith observation, this is how my equation is written. So, now let us go and build a model. So, the function to build a multiple linear model is same as what we used in the univariate case. So, here also I am going to use LM. Now, again the syntax is LM, and there are two input parameters, formula and data. Now, the syntax is slightly different compared to the univariate case. So, I have my dependent variable here, then I have a tilde sign, and how many ever independent variables I have, I am going to separate them with the plus sign. Say for instance, I have two independent variables in my data. So, I am regressing the dependent variable with two independent variables. So, the two independent variables have to be separated by a plus sign. So, now let us see how to do it for our data NYC. So, again I have LM. So, I am regressing price with all the 4 input variables, which is food, decor, service and east, and I am taking these variables from the data NYC. So, you can either separate the independent variables by a plus sign. So, now if you want to say regress price with all the 4 inputs, there is another way you can write the same command. So, I say regress price and then I give a tilde sign and then I say a dot. So, this means regress price with all the input variables from the data NYC. So, if you are going to give all the input variables for regression, then you can go with this, but if you have a subset of variables that you want to build a model with, then you can specify the variables separated by a plus sign. So, just to reiterate, this is the form of my equation. So, now let us go and see how to interpret the summary. So, after having built this model, I am going to look at the summary of it. So, the snippet gives you a gist at the summary. So, if you could recall, in the first lecture of simple linear regression, we looked at what each of this line here means in depth. So, we have the formula in the first line, we have the residuals and the 5-point summary of them, then we are looking at the coefficients. So, here we say that intercept, food, decor, service and east, and these are the coefficients for these variables. So, for each of these coefficients I am given an estimate value, some variance associated with it, a t value which is the ratio of estimate by the standard error, and some probability value. So, if you look at the p value, So, the p value for intercept is very low compared to our significance level, which is 0.05. So, this tells you that intercept is one of the important terms that have to be included in the model. The same goes with the p value for food and decor, they are also less than 0.05, and so we need to retain them, and the stars tell you how significantly different are they from 0. Whereas, if you look at the p value of service, it is 0.9945, which is really high compared to our significance level. So, this tells you that this term service is not important, and if you look at the estimated value, it is very close to 0. So, this tells you that service is not an important term in explaining the price. So, now if you see the p value for East, though it is not very low compared to food and decor, it is, though it does not have a p value which is very low as that compared to food and decor, it is still okay, and the significance star is only 1, which tells you that, hey look, if I have a significance level of say 0.025 or 0.01, then I can reject this term, but till then I can always keep it. So, let us look at the R squared value. The R squared value is 0.628 and the adjusted R square is 0.619, and the F statistic value is really high, which is 68.76. So, this tells you that compared to the reduced model which has only intercept, my full model is performing better and I should retain it. So, now that we know service is not significant, let us build a new model dropping service. So, I have dropped service and I have built a new model, and I am calling it NYC mod _2. So, let us jump on to the coefficient section. So, the estimates are not drastically different before and after removing the service variable. So, this tells you that service is not very important. So, again if you look at the p value, it tells you that these variables are very significant, and if you look at the R squared value here down, so the R squared value before and after removing service has not changed much. This itself is an indicative that service is not helping us in explaining the variation in price. The adjusted R square has changed a bit, and that is only because we have removed one variable and the degrees of freedom change. The F statistic again is really high, telling you that full model with food, decor and East is performing better compared to your reduced model with only the intercept. If you recall from the scatter plot, we saw there was a high correlation between food and service. So, now we built a model dropping service. Let us now retain service and build a model dropping food. So, I have dropped food from here. So, let us take a look at the summary. If you take a look at the summary, though the p value tells you that all the variables are significant, if you look at the R squared value, it has dropped from 0.628 to 0.588, which is a huge decrease, and even the adjusted R square has decreased. So, this tells you that service is less important and food is explaining the price in a much better sense than service. So, the R squared value and the scatter plots tell us to go ahead with the linear model, but we still need to verify the assumptions we make on the errors using residual analysis. So, this task we are going to leave it to you as an exercise. You can do it and verify these assumptions. Thank you.